Good morning, I am Krishna Kumar. Came from Krishna's class. Today we discuss the problem of change of basis and its consequence on the representations of linear transformations. Now we begin with first looking at how the change of basis affect the representation of vectors from a vector space. Now let V be a vector space over a field of F and dimension of V equal to N. I mean, we are just setting up the notations. Let VV and VV prime be two ordered bases for V. Defined by VV is defined by V1, V2, etc. Vn, and this is of course contained V, and another ordered basis VV prime, which is V1 prime, V2 prime, etc. Vn prime, again contained. Now the problem is this: suppose you take an arbitrary vector V belonging to capital V. Now you see that there is a representation of V in terms of the ordered basis VV. There is also another representation of the ordered basis with respect to the ordered basis of the given vector V. So we set up those representations as follows. Let V belonging to V and let square bracket VB, which is a column vector, be the representation of V in Fn cross 1. We take Fn cross 1 to indicate that our representation is not as a row vector but as a column vector with respect to the ordered basis VB. And it comes like this: V has a unique representation in the form x1 v1 plus x2 v2 plus etc. xn vn, and x1 x2 etc. xn are uniquely determined because v1 v2 etc. vn is a basis. And then we define x in Fn cross 1 by the column vector x1 x2 etc. xn, and therefore the representation of V with respect to the ordered basis VV is taken as x. Similarly, x prime is defined by x1 prime, x2 prime, etc. xn prime belonging to Fn plus 1 n cross 1 be the representation of V with respect to the second ordered basis VV prime. Like this, VV prime. Now that means V has the representation x1 prime, v1 prime, etc. xn prime, v1, vn prime. And again x1 prime, x2 prime, etc. xn prime are uniquely determined. Therefore, it determines an x as a column vector. And that column vector represents V with respect to the basis, with respect to the ordered basis VV prime. Okay. So what you have here is VV prime equal to x prime. That's the representation. Now, the question that we are raising is the following. So, this is a column vector in Fn cross 1. This is also a column vector in Fn cross 1. Both coming out of the same vector in V. How these two are related? Now, this is the question that we are raising. Now, we will try to examine this and try to find out the nature of this connection. Okay. Now you observe that, see, there exists a linear transmission on V between these ordered bases. Let this linear transmission be denoted by U, okay, and defined by U of Vj equal to Vj or J equal to, and extended the whole space. In fact, you know that once we prescribe what a map does on a ordered basis, we are defining a linear transformation. Okay, there exists a unique linear transformation with the property that U of Vj equal to Vj prime for j equal to 1 to n, and this is the linear transformation that we are designating by U. Okay, now what you observe is the following. What we observe is the following. We observe that U Vj is Vj prime, and in terms of Bv there is a unique representation for Vj prime that we will write down. Okay, because you know that Vj prime is a vector in V and Bv is an ordered basis, therefore we can write that. So we first do that. Look at this. So let us write it up. Let Vj prime be denoted by be equal to, in terms of Vj's we are writing, this is of the form sigma I equal to 1 to n Pij Pl, where Pij's are the scalars corresponding to this, which in turn means the following, that the representation of Vj prime with respect to Bv is given by P1j column vector Pn. Now this let me designate by Pj. Okay, this is the definition, and that is this. Therefore, each Vj prime with respect to Bv is represented in Fn cross 1 by the column vector Pj, which is defined here. Okay, therefore, now you see that for every j it is defined, that is j running from 1 to, this is clear, absolutely clear. Okay, now let us compute the relation between x and x prime, so that will give the relation. So what you have is that, say, let me draw a diagram so that will clarify a lot of things. So you have V, and then you have two copies of Fn cross 1. I am writing F instead of Fn, I am writing Fn cross 1 to clarify that I am giving a representation as a column vector. Now you see that there is a V over here. Now V gets mapped to two different elements of Fn plus 1, and this is denoted by x, and this is denoted by x prime, and this is with respect to Bv, and this is with respect to B prime. Okay, that's what we have already done, and this in fact is corresponding to a isomorphism from V to Fn cross 1 designated by phi z, and this map is designated by phi prime. That's clear. Now what you are asking is how x prime is related to x. Let us investigate. Now let me write it up. So what I do is I take out these things and then start writing. Keep the basic procedure. So what I have is the following. Now you see that we have already written what these connections are. Okay, so you see that this is what this is actually equal to yeah. Okay, so what we have is this. VBV equal to x. Okay, and VBV prime is designated by x prime. This is what you have. Now you see that V has the representation sigma I equal to 1 to n xi here. Okay, and this also has the representation sigma, let me write j. This is also the same as j running from 1 to n xj prime bj prime. Now what about vj prime? This is equal to sigma j equal to 1 to n xj prime. Vj prime is given by sigma I equal to 1 to n Pij Vn. We have just used this representation. And that in turn can be written as, because you know that the summation here is a finite sum. Therefore, I can interchange the order of summation also. Therefore, I can rewrite the whole thing in the following way. I will write this as I running from 1 to n sigma j running from 1 to n Pij xj prime here. So you see that the Vi's, the coefficient of Vi's in the representation of V is given by sigma Pij xj prime, that is in terms of xj prime. But what is it originally? Originally in terms of x1 prime, x1, x2, etc., xn, that determines x. That is what it is. Write down the details. The details are this whole thing. Okay, therefore, what we observe is this. We observe that xi is equal to sigma j equal to 1 to n Pij xj. This is a crucial relationship. Okay. Now you can introduce a matrix. Define P to be equal to P1 Pn. Pi representing the ith column of the n by n matrix. This is an n by n matrix. So I can write this belonging to or P is given by P11, P12, P1n, P2, etc. Pn1, Pn2. This is the column P1, this is the column P2, this is the column Pn. You recall the definition. Pj is defined as P1j, P2j, etc., Pnj. So this is 1, 2, 3, etc. So I can write here. So there should be no confusion for this. What exactly is this relationship then? This relationship is the following. Therefore, we have the following: x1 prime this is equal to p11, p12, p1n, p21, p22, p2n, etc. pn1, pn2, pnn. Operating over, sorry, yeah, I think this is given by operating over x1 prime, x2 prime, etc. etc. That is the explicit write-up of the relationship. This is can be in short form. I can write this as x is equal to b. Therefore, there is an n by n matrix operating in Fn cross 1. So I will just complete the diagram now. We have B here, we have a copy of Fn cross 1, there's another copy of n cross 1, and then B is mapped to x, B is mapped to x prime, same B is mapped to x prime, and this is with respect to the ordered basis dv, and this is with respect to the ordered basis dv prime, and this is facilitated by a isomorphism phi from B to Fn cross 1 and a isomorphism psi from B to x prime. Then what we have shown is that there is a n by n matrix which gives a representation, which connects the representation representing vector x prime with x. All descriptions are carried out with respect to the basic ordered basis that we have chosen B. Okay, so this is the picture that emerges. So let me just mark this with a color so that this mapping connecting B to B prime is represented like this, and this is designated in the field box. So that's the connection between the representations of V with respect to the ordered basis BV and BV prime. Okay, so this is an ingredient that we need for the next stage. Now we have explored the relation between the representing vector of V in both, in Fn cross 1 with respect to the ordered basis BV and BV prime. The next stage of our analysis is connecting the representations of these of the vectors in of the linear transformation that you define from one vector space into another. Okay. So we start with second stage of our analysis. The second stage of our analysis starts by connecting the vector representations of the order basis, or looking at a linear transformation and going for its representation. Okay, so the scenario is the following. You have there is a vector space. We first take up the simple case. Look at a T belonging to L. That is, both the domain space and the range space are taken as the same. And then we have the ordered basis BV and the ordered basis BV prime as defined earlier. Now the question that you ask is this. Okay, we keep the same basis for the domain space as well as the range space. We are not going to change it. We'll take a more general scenario in the next stage. So we have T is a linear map from V to VV, and then V has an ordered basis VV. So we have a certain matrix representation for T with respect to V. Let matrix representation of T VV may be designated by A. Then A is a and n by n matrix defined by or I write as with components with entries. That is A equal to, by Aij we mean the entry at the ith column J3. Okay, so this is an n. Then we have the following, that is V for TV, the representation of TV with respect to the basis BV, this is equal to A times the representation of V, that is okay, right? So this is the relation. So A is an n by n matrix, and this is an n by 1 matrix, and this is again in so the representation of T, or the matrix representation of T with respect to the ordered basis BV is given by A. Further, suppose we take look at the representation of the same linear transformation in terms of the changed basis, then this is going to be which can be written as some B times, where B is an n by n matrix, okay, where B is equal to some Bi. This is an n by n matrix. This is the scenario that you have. So we have these two relations, namely, this is the one, this one picture that you have, and the other picture is this. So A and B are different. Now the question that we are asking is the following: how A and B are different? Okay, let us explore this. A diagram will again help you to see, visualize properly what is going on. Okay. So you see that V is the vector space, and we are talking about linear transformations from V to V. So V is here. This is the weight space V, and T is. So T maps V to T in the abstract space. Now we have the representations here. Fn cross 1, 2, 1. And V has representation here given by the following. We have designated it. So this is with respect to dV. This is, of course, designated by V. And now there is the corresponding representation for TV. This I write as PV with respect to V. We use the same notation. Okay. Now what A does is to map VDV to TVV, or this is designated by T. That's the scenario. Likewise, we have another picture parallel to this. You have another copy of Fn cross 1, which is isomorphic to V with respect to the ordered basis VV prime. Phi prime. And then So according to our notation, this vector is V with respect to BV prime, and this vector is TV with respect to BV prime. Okay. Now there is the map from Fn cross 1 to Fn cross 1, connecting the representative of V with respect to BV prime with the representative of TV with respect to BV prime, and this is designated by P, which is equal to P prime. So this is the picture that you have. Now what you are asking is the following: how B and A are related. Already we have done some work. What is the work that we have done? We have seen that there is an n by n matrix which connects V BV prime with V BV and denoted by P. Okay, so you recall it is an invertible matrix which carries sorry. Okay. So VBV is P times P operating over VBV prime. Similarly, you have the following. Similarly, we have the following, an analogous relation. These two relations are there. Now we are going to connect them. Okay. What? Let us examine this in our diagram. Our diagram will clarify this. This is the picture that we have. See, we are going to connect A with B. A carries VBV to TVBV. But the same thing can be achieved in the following way. Going from VBV to VBV prime and then mapping with B, you reach here, you reach TVBV prime and then pulling it back using P to TVBV. So let me write that relation. And we shall prove this. The diagram. We have we will examine this. What is this? This relation we have, right? Or TVBV is equal to TBV acting over this one. So we will work that. Okay. Now we start from here. Okay. So we start slowly replacing things in terms of BV prime. Right? Okay. So let us start doing it. What is BV? BV we write in terms of BV prime. Okay. So that's equal to, because you know that the map P is defined in this way. Therefore, P is an invertible map. So P inverse carries VBV to VBV prime. So you see that this is equal to P inverse VB. Okay. So VBV equal to P of VB, which implies, okay, then now let us start working this. So from here we go here, and from there we go here, and then from there we go here. So let us start working. So VBV I write as, okay, PBV, PV, prime. So let me start here. Okay. This is equal to what? P inverse of okay. Now TVBV prime is what? TVBV prime is equal to TBV prime BV prime. Okay. Now what is that? Again VBV prime we shall write in terms of VBV. So what you get? VBV prime is in fact so this I can write as P inverse of did I write this properly? So I have written TVBV equal to TVBV prime. So this is in fact, I write this as, I'm sorry, I think this is P of TVBV prime. So TVBV is essentially P of TVBV prime, right? Therefore, this is equal to P of TBV prime VBV prime. Now that's equal to P of, and VBV prime I write as P inverse of therefore what do I get? So I get this relation, fine. Okay, this I can write as P but we already have TVBV prime equal to TBV acting over BBV, and this is equal to TBV acting over because TBV equal to TBV VBV. We are using star. So what do you get? So together now we can connect. So let me leave the figure here itself, or I can remove this and then write. Therefore, what do we have? We have the following. Okay. PT B prime B prime P inverse is equal to, what is it? P so in our notation, this is what we can write it in terms of A and B. Okay. So P, the matrix representation corresponding to TBV prime is P inverse or equivalent B is equal to what you have now. You operate with the P inverse there. So P inverse A. So both are equal. This gives the connection between the two representations of T with respect to the ordered basis BV and BV. Okay. So that we have worked out a simple scenario. Assuming that the ordered basis assuming that the range of the linear transformation is the same space. Now let us generalize this. Now we shall generalize this. We assume that range is an m-dimensional this assumption. T is an m-dimensional vector space over, that is the range. Therefore, T is now from where dimension of E equal to n, dimension of W equal to. Now you see we are having four different, there are two different ordered bases for V as we have introduced earlier, and two different ordered bases for W which we shall designate. So let us fix the notation. Ordered basis for V in domain space as defined area. Let BW n and BW prime be two different ordered bases for W. Then if W belong to W and be the vector representation of W with respect to W and is the vector representation of then there exists an m by m matrix Q belonging to such that this is equal to BW. Now the analysis is exactly as we did in the case of heat. How in the case of now T is represented by an m by n matrix be the representative m by n matrix of T in defining a map, the corresponding map from that is, this is the situation. T V with respect to the ordered basis BV is given by T with respect to TV with respect to the ordered basis you are in W, therefore BW is given by the representation for T with respect to BV BW of acting over V B. is the connection. Okay. Now similarly you have a relation between the two. Similarly, with respect to the order basis, BB prime and BW prime for B and W respectively, the representing matrix for PV with respect to BW prime is given by the representation of T with respect to BV prime, BW prime. This is an M by N matrix acting over B prime. Let us take the help of a diagram to understand this. So you have B, you have W. There is the element V, it's mapped by T to T. Okay. Now what you have two linear, two ordered bases that we introduced for V as well as for W. This is this is n dimensional. This is n dimensional. Now with respect to BV and BW, you have the images of M cross 1. When B is mapped, this is phi BV to the vector B in Fn cross. And then PV has the analogous image here. But now this is with respect to BW and the corresponding isomorphism psi between W and Fm cross 1. And let this be designated by BW. Now you see that you have the M by N matrix denoted by T W, BVBW connecting VBV to TVBW. Okay, so what you can designate it by. This is not the same A as you have because now it's a general scenario. Now let us take the corresponding picture for the change of basis. What you have? You have another copy of Fn cross 1 and a copy of Fn cross 1. Now what you have? This is created with respect to the ordered basis B prime, and then you have the image given by V BB prime. Similarly, you have the image of TV BW prime here, and you know that this map is carried out by the isomorphism phi prime corresponding to BB prime. This map is carried out by the isomorphism psi prime corresponding to BW. Now you see that the map connecting the representative of B with respect to BB prime and the representative of TV with respect to BW prime is designated by this is the same thing. But you know that there is a map P as before between Fn cross 1 to Fn cross 1 connecting B BB prime and B BB. Okay, so let us designate this by and the direction is not okay. Similarly, you see that there is another invertible map, let us designate it by U, connecting TV BW prime with TV BW, mapping TV BW prime to TV BW, and Q is invertible. P belongs to and Q belongs to M cross M. This is the picture that you have. Now let us see how how A and B are related. This is the question that you are asking. Okay. Let's work it out. It's very interesting to see how these things turn out. So what do we do? See, we have got TBVBW of BB. Okay. So note the following, that this is equal to P that means you are mapping this, which you have as A. So this is one relation. Now let us work out the same relation. Now I can write BV or VBV as what? P of okay. Now I apply T dv prime dw prime on that to carry that vector to here. So what do I have? So suppose I apply T dw prime over then this is equal to T dw prime P dv. Okay. Now what one does? You apply, so we have reached here TVV which is equal to, and this one is essentially equal to T TV this is equal to TV of dw prime is essentially this one. So now let us use this. Okay, so this part can be rewritten in this particular form. Okay, so what do I do? So I have started with dv, reached here applying what do you call it? So this I wrote as P of this vector. Then I apply T dv prime. I have reached here, and now I can rewrite that. This is the one. So I have dv dw prime. This is equal to this vector. This is equal to Q inverse of dv dw. Now put all these things together. Okay, right? So you get Q inverse of dv dw equal to Q inverse of this, which you can rewrite in terms of all this. Therefore, what one does? Now this is equal to TV BW is what? This is equal to T BV W acting over TV. Okay. VBV I have as VBV prime. Okay, so I can write that. So this is equal to. So this is equal to Q inverse T BV BW prime. Sorry, BW. VBV is P VBV prime. So this is equal to P prime. So TV BW prime equal to this. But what is this? See, TV BW prime is equal to T BV prime BW prime V BV prime. Okay. Now putting them together, what do you get? Hence, we have used that result. This is equal to, we'll mark that out. And that's what you have. This is equal to TV W prime, and that can be now written in the form. This is equal to this is equal to this one, that we have Q inverse TV BW P of This is true for every V. Which implies or what is this? This we have designated by B. B is equal to Q inverse A So we are computing this. This is essentially, you apply first P, reach here, then apply A, and then apply Q inverse. That's a proof of that. So this is the connection between the two representations in terms of different ordered bases. This is a general scenario, but we will be mostly interested in our work on with both the domain and the range kept as the same vector space. That means W equal to, okay, this you can quickly check whether this relation could be right. What about B? B is an this is an M by N matrix. What about P? P is an N by N matrix, and then this is an M by N matrix. Then what you have is Q inverse is again an M by M matrix. And you see that this is eminently plausible. Okay? Because this matrix multiplication is well defined. And this is the connection that, okay? Right? And you see that as a special case, what happens is Q equal to P. So in that case, you have B equal to P inverse A. So that completes it. I think I'll stop here and then probably demonstrate working out some examples with them. Okay? So for the time being, we complete this talk here. So thank you very much.